My name is Maciej Perkowski. I work at Nordic Semiconductor. I am a software test developer. You can find me at GitHub, and my handle there is Permac. You might also see me on Discord answering some of the questions on the testing or Twister channel mostly as Maciek. And today I would like to talk to you about Pytest test in Twister. The overview, we're going to start with simply answering why we even bother about talking about Pytest. Since we have Twister, what do they have in common? Why do we need it? Also a bit what is Pytest, how it is integrated with a Twister, and then I think what will be the most interesting will be the examples of how we are already using it, and maybe a bit shed of a light what we're going to do in the future, what we can do in the future with it. So obviously, why we even bother with it? And the bold statement is we want to improve the quality of Zephyr. This is like always nice with testing. You always hear test supposed to improve the quality of your software. But it's not all about the quantity, it's really about the quality. So we really want to test some new stuff that were not possible before with Twister. Because on its own, Twister supports quite restricted or limited workflow. Twister builds your application, it flashes to your device or starts the emulation for you. And then it only reads for the output from your serial or your fan in, fan out. So it doesn't allow to really interact with your test or do anything beyond this workflow. So, but of course, we would like to do something more. What if we want to be more Pythonic? What if we want to use some cool Python libraries that are there? Z-test and basically like tests in Twister that were existing, they were really focused on the C side of your application. But what if you want to be more Pythonic? What if you use those libraries there? Also, what if you want to communicate with our device during the test? It was not possible before. It seems quite obvious that, I don't know, if you're having like a shell application, you'd like to test, to give some input to it, and then read what will be the output. It was not possible before. Also, especially if you like to do some more setup, you want to do something on your host side. Maybe you would like to start virtual server on your host that will be talking to your client app. Now it will be possible, and I hope I will show you in the further examples. Some extra tooling that you might use from the CLI, like MCU Manager to program your board to interact with the programming, or using CAN interface for communication. Or even further going on if we would like to use more than a single device talking with each other. So is it possible? So this is why we start thinking about adding Pytest to the picture, because it's quite popular framework. It's very often used in the Python community. And according to their documentation, it is a mature, fully featured Python testing tool that helps you to write better programs. Also, Pytest frameworks makes it easy to write small, readable tests and can scale to support complex functional testing for application libraries. So it's all quite bold statement. It's basically that's what we are all looking for. Is it true? I hope that after the presentation you will be convinced that yeah, this can be true. So for the main features for Pytest, at least in my eyes, there are like two of them. Plugins is really cool feature because those are modules. They can implement hooks, and your plugins can hook into the module, into a certain place in your application, so in your framework. So like you can imagine you have like a place where you're collecting your test, and then you have a hook there. Your plugin can go in and do something, like maybe change the ordering of the execution, or maybe decide how to parallel the stuff, or maybe apply some filtration. Also, you can apply the hook on the other end. When the tests are done, you have your reports, but maybe you want to have the report in the other style. So hooks allows you to really easy inject some pieces of your or other modules to do some stuff with your data, with your tests, or the framework itself. And in fact, that what I'm going to be presenting is actually a plugin to the Pytest. So the integration with Twister on the Pytest side is done as a plugin. So you add a plugin to Pytest, and it allows to recognize what Twister wants from it. But in general, plugins, in our view, won't be that interesting because they are mostly focused on expanding your framework, whereas, as you'll see in a second, Pytest here is just an executor. Twister is a full framework. For us, the most interesting part will be fixtures. They initialize test function. They are really test-oriented. So they provide you building blocks that you can reuse in multiple tests. They have very explicit namings. They are really easy to pull into your test. You don't have to think where they are located. You just really use the name in your test that you're going to use this fixture, and Pytest will do everything for you. Also, they are very modular. One fixture can consist of many other. They can build full stacks of them on top of each other. And they scale really well, both in complexity and also in the scope. And also what is very interesting with them, they provide a safely managed setup and teardown for your test. On this slide, I wanted to present what is the general idea behind how the Pytest was integrated with the Twister itself. This block presents like the generic workflow of Twister, where it first collects the test based on the YAML files, and on the left you see an example of such YAML file. And then it generates the test configurations, apply filters, spawn workers, and then start the cycle where the application is built, executed, and verified. So when we are up to the execution, the main question is being asked, is it a Pytest test or not? If it is Pytest test, then Twister will prepare and call a very certain command for the Pytest as an executor. Pytest will do some stuff on its end, like flash the device, interact with it, collect the results, and then as the output, it will prepare the JUnit XML report, and Twister will read this exact report and parse the result out of it. So the communication as an input is a very specific command for Pytest, what to do, and then on the end, we are looking at the JUnit XML report. So the integration is at this kind of level. Pytest runs here, it's put like in a different color because this runs as a sub-process. And the idea behind it, like the requirement was that it should supposed to be like very seamless experience for the user. On this slide, I'm just showing you the typical Twister command that you're gonna call, pointing to a location where our test is sitting, telling that we're gonna run it on native POSIX. And then basically it looks like any other test from the Twister user perspective. What is highlighted here is just that you see that there was a test passed in less than 2 seconds on native POSIX. And that's it. So it looks like any other Twister output. So you don't know that was even Pytest in the background. But however, this is the place where actually you start seeing where all the seams are. Because it's supposed to be really seamless for the Twister user, but it's not that obvious from if you're coming from the Pytest community or more like how it is developed. Here you can see all the seams. Because what we are doing, we are calling in a very specific way. If you want to replay the Pytest test, can you do it on itself without Twister? Yes, you can. Maybe it can be a bit more complicated, but not that much. First of all, the easiest way would be to call Twister with extra verbosity to give you this exact command which is using to call Pytest. So for instance, you would like to just tweak with your test, run it multiple times. You don't want to wait 15 seconds for all the collection and all doing on, but maybe like just 2 seconds to get the test results. So you can call Pytest on its own by copy-pasting this command. And in this command, there are several interesting parts. The first, this command actually is like combination of 2 commands. And you don't see my mouse, but on a second line, will it work? Sorry. I see. Here, in fact, these are 2 commands. First one is exporting the location of the plugin to the Python path, so the Pytest can pick it up. And the idea behind this was the requirement was that it's supposed to be really seamless, and Twister is developed as a part of Zephyr. You would get it by checking out the tree. You install nothing. And this was also the requirement for the plugin. You don't want to install it. You don't want to handle which version to use. It should come as a part of a Twister itself, as a part of the Zephyr tree. You don't want to install it, which is also maybe a counterintuitive to what people dealing with Pytest are used to. But then Pytest is being called. We are telling that we're going to use Twister harness. Also, what is important there that we're going to tell where the build directory is, so where our application is located, so where it can pull it in. That we're going to need this JUnit XML report so that Twister can read afterwards. Some logging parameters. And also, in the end, we need to pass what type of device, so which adapter will be used. Will it be native POSIX or will it be hardware? And of course, obviously, that we're going to need our plugin that we wrote for Pytest to understand what Twister wants from it. I mentioned that you need to pass what type of devices, and this leads us to the idea of device adapter we have in the plugin itself. It's nothing new because all of this, you also have it on the Twister side. They are called like handlers, but we do a bit of refactoring, a bit of more abstraction to get a bit better in our eyes organization to allow for easier expandability of adding new adapters instead of like copy pasting. So at the bottom level, there is device adapter, which is an abstract base class. So it just provides you the ideas for the methods you're going to use. And this is not a full class, it's just a snippet of the code. So you can have a write method, which is responsible to write data to your device. It's going to check if device is connected. If not connected, it's going to give you error. And then it's going to use this kind of internal method called write to device. And the write to device is an abstract method. Abstract method means that if you don't implement this particular one in any module or any class that will inherit from that one, you will get an error. So this is a method to make sure that your interfaces are aligned. Because in your test, you will just going to call dut.write, and you don't want to bother if it's like qemu underline or is it hardware. Because below, you can see that they are the real adapters. So for hardware adapter, write to device will use a serial connection and write data there. For qemu adapter, the fan in, fan out will be used. The next interesting part of the usage of Pytest are the fixtures. And fixtures are these core building blocks of your test that you can reuse in many other. And here is like an example of some of the fixtures that are already implemented for you in the solution. So first of all, you need to mark that a given function will be a fixture, and you will use a decorator, pytest.fixture. And you can also provide what will be the scope of the fixture. So how long should it live? Should it be only set up once for the whole session? So each test will use the same fixture, or maybe it should be each time for every test, setup and tear down should happen for each single test. It will make maybe more sense on when we are looking at the real test. And the fixture, it's also preparing you like the setup and tear down. So all these parts up to the yield part is a setup. As a setup, we will try to figure out what is device type being used, and then pull the proper adapter using the factory, and yield this device object. So this is like a setup. Then yield returns the object to the test, and after test is done, the code is coming back here. And the finally part is going on where we make sure that device is closed after the test. And with this example, I wanted to show you that the fixtures can be also modular, because as you see, this DUT, device under test fixtures, it uses the device object, so it's using the one from the top. And also they can have quite a configurable properties. So if you look here, the scope, it's using determine scope variable, but in fact this variable is a function. And this allows to decide from a top level, like if you declare in your test YAM that you would like to use a given fixture for the whole session, so you don't want to reflash your device every time for every test, but maybe you know what you're doing, you just want to like reset the device between each test, not to waste time on flashing, you can define the other scope like the session. And this will be figured out based on this mechanism. And again, it will first pull off this device object. And the difference is that this fixture DUT will launch the object for you and return the object which is supposed to be already prepared for the test. And at the end, it will initialize the close procedure. So finally, we came up to the examples of the tests. So we can have a shell interaction test. And this is not the real test for the shell module. This is like an example how the shell module can be used in your test. Because here, this is like a full file of the test. And as you can see, there are only like 2 methods. We're only probing a minor part of the shell module. Also, what is interesting that to get a fixture, you just use it in a test definition. We are importing the shell class, but basically just to give the syntax for the typing and to help our IDE to pick up which are the properties of the shell. But you didn't even have to import the shell. You just use the name shell, and Pytest will figure out. It will have the list of fixtures that will define for you, and you will be able to use it. And the shell fixture is one Another layer is built on top of the device fixture, and it just adds some extra handling, giving you methods for read and write over UART, over the shell. And in principle, that you just going one step further, so your device is ready when we get the prompt. You have a prompt, and this is the moment when you can start your test and start interacting. And here, this is very straightforward. We use this shell fixture to execute command help. So this is like it will use a write to our device. We get the output as lines, and then we're going to assert that somewhere among the lines we have the available commands, and our test is passing. And the other one is basically doing the same. It's just using the other command. We are executing command kernel version and try to verify that among the output we have Zephyr version string printed. So to see it in action, this is just a sorry. Maybe it wasn't the best idea to use this kind of interactive outputs here. If I just turn it off and turn again. Okay, doesn't matter. Well, what I wanted to show you on that slide was that in the output you will see quite a nice, so if you call with extra verbosity, you can actually see what is going on with your, nope.
You can click on the shared screen.
Okay, let's not waste time on it. Sorry for that. I guess when I switched to the pointer, everything crashed. So yeah, basically here I wanted to show you that how this test looks when you look in the output. So if you look at the output, if you run it, you will see that there is like when Pytest is kicking in, it will first print you the lines that, okay, this is a setup session. We're gonna wait for we're gonna use the hardware device. We are waiting for we're gonna use a certain device, certain port where we will communicate. And when we get the prompt waiting for us, this is where the test can kick in. And then we will do testing. You will see that we send an input to the command, all the output that came out of the command, that output was successfully verified, and then we can do the teardown procedure. And also what I wanted to show you on this example, that here with this fixture, they don't define the scope. So by default, it is a test, it is a function scope. So every single test will have its own setup and its own teardown to like keep the isolation of test principle. So we will see that flashing is happening before every test. Another example is that, so what more you can do? So the first one was quite simple, showing how you can interact with your shell. The other one is a bit more complex, showing you that you can start doing some more stuff, actually start doing stuff with your device. And this is an example for testing MCU boot, so the bootloader, and the test is using MCU Manager, so the CLI tool that provides you interaction with your device. And this is an example of test downgrade prevention. And this is only a couple of lines out of the test. It's not the full test. And again, I'm going to focus, it's going to use the device adapter. It will use the shell. And also it will use the MCU Manager. MCU Manager fixture is also defined in the top level for you. And this is just a wrapper over this MCU Manager CLI tool to simplify. You don't have to write every time exact command what you would like to do, but it's just wrapping over the most typical interactions that you would like to do. So in this test, we will use a shell to first check out what is the version of the application we built, and if it's matching the one from our configuration. Then we will call create sign image, which is using West sign and in behind to sign your image with a certain version, and this version is lower than the original one. We have to disconnect from our device because MCU Manager will use the same serial line, so to be able to get a connection to it. MCU Manager will do the image upload and reset the device, and again we'll have to connect to get the output. We are reading the output until we see that the launching primary sold application, so basically the whole procedure ended. And also we want to verify that in our output there are no lines that will match starting swap using move algorithm, so we will make sure that the swapping mechanism didn't start it. We actually want to make sure that the line erased due to downgrade prevention happened. And at the end, just to be sure, we would like to verify that when we ask through the shell what was the version, this is the one that was at the beginning, that the downgraded one wasn't applied. So it's already showing you that you can do a bit more, not only talk with your shell, but maybe also use external CLI tool to also do something with your device. And in the end, I think it's the most complex example, which is I think really interesting because it is a full end-to-end test. It is using the LWM2M, and it's the test for interoperability, and it is using the Leshan demo server. What is really nice that is based on Open Mobile Alliance specification. I really recommend you to go to that link and to see how it is implemented. There is really nice README file there, also pointing each certain test from the specification one by one, is it implemented or not, and all of them are implemented. Also, they provide you the ways and describe how to be able to reproduce the test, because it requires a bit of extra tooling, how to set up your virtual network. You will need also like this Leshan server and other tools, but luckily they provide a handy Docker image that you can, and a quick description how to use it, so you don't have to install all of this stuff for you. And what I wanted to focus is this test is really full end-to-end. So we will have our virtual network that is controlled and started by Pytest with Twister. Also inside there is sitting this virtual Leshan server. There is also the device under test, so our client application. And it can be, in this test, it will be qemu or native POSIX, but in fact, it can also be like real hardware. This is the scales or can be used on other devices. And server will talk with the client using multiple protocols, but also our test can be talking with a server with REST API both ways, and also communicating with the client both ways using the shell. And to just show you how the test looks, this is using the nomenclature from the specification, and the test is using the shell, so the one you already see. It's using the device adapter that you see, but it also introduces the Leshan fixture, and Leshan fixture will start this virtual server, do all the setting for you, and also it will use an endpoint fixture, which will create the endpoint for you. And this is an example of the registration update test. And in it, we will use a shell. We're going to push a command LWM to read 101 to our client. So basically, we are asking about this address. In this address, the lifetime is supposed to sit according to the documentation. So we're going to read it as our output. And the first line in the output should be this lifetime. Then we're going to modify the lifetime, just adding some value to it. We're also going to read what is the current time. And we're going to use the server. We want to write to the server, to our endpoint, to the 101 location, the new lifetime value. So we are pushing the updated value to the server, but then we are again reading from a device until we get update done. So server will push the value to the client, and on the client side, we are verifying if the update happened or when it happened. And again, we're going to ask the server to reach to the client and on a certain endpoint to first get the output, and among the output, we want to see where actually was the last update. So we want to verify that the value of time actually matches the time when we send the update. So it's not somewhere from the past, it's not somewhere for the future, it's actually aligned with the moment we send the value. And also we want to verify if this lifetime is the lifetime we updated to. So actually if all the process happened as we wanted. So as you see, it's like we can interact with multiple agents, with the server, with the device. They both talk with each other. So it's really like full end-to-end test, finally possible. And maybe what is interesting to highlight here, that I hope this maybe it's clear that this kind of test is quite readable. And if you really take like the specification and all the steps which are in your specification, like a cookbook, here's all the like implementation of it, all the steps that the test is doing. So I think it can really, of course, there's a lot of stuff going on behind. You need all of those fixtures and they do the stuff for you. But I think that it can really allow to give a really simple framework to script all these kinds of interactions. So what is the future? Of course, we would like to start adding more tests. There are not that many tests using Pytest added. I think it's in the tree for maybe a year, but there are not many tests yet using this tool. There are also, I believe, many low-hanging fruits that are, in particular, that use shell for different stuff. And you can find many of them marked using harness keyboard in the YAML, because this was the way before to just tell Twister that actually we don't know how to execute the test because you will need some interaction. So right now you can just, in many cases, you can just copy paste the shell example, which I showed you before, just replace the values you want to put in your input, the values you'd like to verify, and you might be ready to go. Also, we'd like to test more protocols. I have a quick chat with Briggs. He's apparently already working for using Pytest for testing the CAN bus. But of course, there's more and more. But not everything is possible yet. Like the topic which is not properly addressed is handling multiple images. And especially if, of course, we have sysbuild that allows to build multiple images, but we want to go a bit further. Like we want to reuse the images between different tests. For example, if you have your Bluetooth test, when you have your central and peripheral, you don't want to rebuild central every single time. You want to build it like once and maybe using different variation with many different peripherals in different tests. So this still will need to a bit more thinking how to add this layer to Twister. Twister doesn't support it yet. And further, having multiple devices. What I show you, all of them were using just a single device under test, but maybe at one point you would like to have multiple devices talking with each other. What I show, it's possible to talk with a host. It's relatively easy, but if you have two devices, it's not that straightforward yet. So to summarize, I believe that the integration Pytest with Twister opened really new levels of testing that was not possible before. I hope it can have a pretty low entry level. There are tons of tutorials on the Pytest itself. We also try to make the plugin very simplific for the end user. It also allows to like already pull many existing fixtures ready for you to use. You don't have to figure out how to configure your device, how to set up your serial, or should you use a fan in, fan out, or should you use serial connection. It's all there for you. So this is DUT type agnostic thanks to this device abstraction layer. Also, it's easily expandable. If you would like to add new type of device, then you can just either copy paste the existing device and modify the methods which is using, or use this abstraction to get it there. And the same for fixtures. You can have fixtures in tree, you can have fixtures in your user module, or even if you're just downstream application. And the fixture itself, they are really scalable, so they can do really small stuff, like provide just a string into your test, but also quite complex things, like setting the whole server and the whole network. They are highly configurable. They are also modular, because as you see, they are all sitting on top of each other. And they are also very reusable, because every single test I showed to you, where it's using like a shell fixture is using duty fixture, and so on. So this is also an easy way to give you a building blocks to play with in your test. And they also are quite nice if you want to do a setup and tear down. Unluckily, you didn't see the output, but it nicely points to you that this fixture was used on top of each other, all the stuff that they're doing. Now you're within a test, and now the test ended, and this is like a tear down procedure. So it's like winding and unwinding in a certain order. And just at the end, some helpful links. And that will be it. Thank you for your time, and I hope you have some questions for me.
Hi.
Hello.
Have you ever used or do you envision using this test framework for reliability testing? Let's say you have a new hardware version or a new firmware version, you wanna stress test it, like test all the interfaces at the same time, reboot it like 1,000 times, like power cycle, see if it's gonna survive, like longevity testing, reliability testing. Is that a good framework for that, or is that a different use case?
No, I believe it can be a good framework for it, certainly. I mean, I haven't done it. There are no tests like this, but yes, certainly. You just, because it's really up to what you can easily script in Python. Like here with this fixture, like if you look at maybe the shell example or downgrade prevention, with this fixture you already get with the device which is pre-flashed for you. But maybe you want to go to the lower layer, which you can do actually, like doing disconnect and connect. Maybe you just can do a loop. I don't know, connect, disconnect to your device multiple times until you get an error. Or here in this shell test, maybe if you want to stress your shell, you can just make a loop over the shell execute command and I don't know, looping 10,000 times or looping for an hour, putting the information then and out and think if it's going to fail or not. So certainly you can quite easily, also thanks to the Python, you can quite easily script all different types of testing. Thank you.
Have you experimented with using this with like a native sim test running within the PC? And if so, when you were receiving serial console traffic, could that also be tied into the dummy shell backend?
Most likely, yes. I haven't played with it, but surely, because like here, if you have this shell fixture, that particular one will use your device, and device is using this device adapter. But you can exchange like these pieces somewhere along the line, and instead of like using the real shell, you can. I guess what you're asking, you can do like some mock or some stub for your shell interface that it will be in a loop. So even like if you want to do this adapter, like here. So I guess instead of writing to real fun in far out, maybe you would like to replace it with some dummy function that will provide the functionality you're looking for. Is it what you're asking?
Yeah, so I'll leave the microphone again. In the native sim test with the Zephyr shell backend, it's possible to basically inject text into the console, then read information back out from it. There's a sort of a glue interface for doing that that's provided. I think being able to hook that into this would be pretty valuable because it's much easier to do regex and text-based parsing validation in Python.
Yeah, definitely. I'm quite sure that it should be done. I won't answer you to exactly how it can be done, but afterwards we can discuss, and I'm pretty sure it can easily be done. And yeah, regexes are quite nice in Python. My colleagues often, you can use the existing methods, but you can also use your own one. Like you see in that example, they like just write the method over using the like match no line or match lines, right? So to give you some user-friendly interface for this.
Yeah, I'll try to look into it because it could be pretty powerful. Thank you.
Yeah, great.
So to speak to the earlier question about stress testing, we don't use Pytest, but we use another Python test framework, Behave. But we do a substantial amount of stress testing on our hardware using very similar techniques. And then as far as to the talk, I think it's great that more people are trying to make hardware testing and firmware testing more and more approachable and easier, lower the barrier to entry. So thanks.
Yeah, thank you for your comment. And also maybe to comment back what you said, that yeah, people already have solutions for this. And like internally, we have a huge amount of like proprietary testing tools. So those kind of tests were doing already proprietary. Like we have a means to do a Bluetooth connection and test it. But what we are really interested in to provide a tool that it's rather lightweighted, that first of all, it's like tuned to work the best with Twister, and which is also like open source, because I believe this is the greatest value. If the users actually can start writing their tests, they can actually start executing their tests on their setups, and it's not like the company have the way to test the Bluetooth, but it's actually like the part of the native framework which is used in the open source. So that was our main motivation here. Thanks for your comment.
For the lightweight M&M sample and test you showed, is that starting up a local server?
Yes.
So is this test using like a local Ethernet device? And do you have a solution if you wanted to test with a cellular device that's on the internet?
So first of all, I won't be able to answer all the details. I'm not very familiar with this, but I think they have quite a nice description of what's going on if you go there first. You can also contact the developer like Seppo Takalo. I'm sure he will be happy to answer. But then going further, basically what I wanted to stress during the presentation, that you can kind of exchange these pieces. So right now it's using this virtual network and the protocols here, but nothing stands there. You can, instead of this, when you configure this virtual server, maybe you would like to use actually the real one that can do the stuff for you. And then instead of using this virtual connection, use the, like you asked for, cellular. Okay, yeah, that the one. So yeah, and also like for, and this is running on qemu or native POSIX, but it should be also quite straightforward to, I mean the same test should run with hardware. If you do the proper setup, the test doesn't have to change at all.
Thank you.
Actually, following on this line of questions, so if we wanted to run this on hardware, essentially, then the DUT would be the same because the device adapter hides those details, correct?
Yes.
But the lesson in that case, probably we will need to tweak it so that you'd have another version. And then if you want to go over the internet, of course, I'm assuming, like you said, that the setup and teardown methods where I can, like in here, for example, I'm assuming you're spinning up the Docker image and
so the Docker image is spun by the user before the test.
Okay.
And I believe it just gives you like the server running in that you can communicate.
Right.
It's open the ports and you can talk with the server.
Yeah, but there's nothing preventing you from doing that from Python as well. If you
No.
Okay. Right.
I mean, yeah, you can just add a script that will start the Docker server and everything for you. Yeah.
And do you have entry points for like test suites in the sense that, for example, such an initialization routine, then it will only be executed once for all LWM10 tests?
Yes, this is actually, maybe I forgot to talk about it, but yeah, this is the great point. So this is particularly because this is also like an interesting story. Like Seppo was one of our, let's say, first customer, and we use this type of a test as a user story to kind of figure it out what would be interesting for the community and what kind of test they would like to do, what kind of functionality they would do. And in like the early version, we stick with this principle of having the test living in isolation and having the setup and tear down every time. But obviously he started asking like, okay, I don't want to start my server every time.
Right.
I just want to start it once. And the same, I don't want to flash my device all the time. I just want to just reset it. And yeah, definitely there is a way to it. Like in your YAM file, I don't have it in the slide, but basically if you have like this section where you have this harness configuration,
yeah,
you can add extra parameters, like you can add Pytest root. But I think it was also shown in the here. You can have you can have a DUT scope in your YAM, and that it will tell you, in DUT scope in particular, it will tell you like, do you need to set up your DUT only once before the all test session or for each test session? Like, and it's functioned by default, so one test, but it can be the whole session. Okay. So this is what I meant, that these fixtures can be nicely configurable, and they have a nice scope. You can define if it's only for very short amount of time to live, or if you're gonna to live for the whole session.
Yep, thank you. That answers the question. And then the final question, just to be clear, that if I understood the sequencing, so Twister DOS runs as usual, and it's just at the end that that Pytest is executed. And because what confused me is that is Pytest test no, then you flash. So when is it flashed for Pytest then?
Pytest is doing flashing.
Oh, Pytest is doing the flashing.
Yes.
Oh, okay.
So basically we have to like step out of the twister, because also what we also realized during our tests, like especially like with this MCU manager, this was another example why we really wanted to have Pytest there, that we would like to do more stuff. We don't want to be flashed once and forget about and just read at the end. Maybe we want to reflash or do reset to see if you're gonna update or not. That's why we added a bit more functionality to the device side. So if you
So in the MCU Manager 1, you had I think reset, but maybe not flash in the code. Reset device.
So it's reset, yeah. So in this example, the device will come firstly flash already, because this is like the default what the Doot setup is doing for you. But then we are using MCU Manager to send the update to the image.
Okay.
But yeah, certainly you can do a bit more with it.
Thank you.
I think we have time for one last question here.
I'll be quick. Is there a convenient out-of-tree way to extend the device adapter factory, or is that what's the expectation there? If you have a custom simulation platform, you want to create a class for
this
that?
is, and we will be really glad. We will be really happy to support you if you want to add something. We hope we made it in a way that it should be really easy to extend. Like we try to do the abstraction, so at the base level you have this device abstraction, but then on top of it you have like the binary adapter, and on top of it you have like native SIM or qemu, because depending what stuff are common, so what is common is on the lower level, and only the stuff which has to be replaced are on the top level. So I believe if you want to use your own, I don't know, like instead of calling a certain executable, you would like to call different executable, or instead of using FIFO file for communication, you would like to, I don't know, use something else. And I think as long as you follow these abstract methods that are required to have, then it will work. Of course, you can, maybe you will need to like stop the method, and because flashing doesn't make much sense in the terms of qemu. Yeah. But maybe it's replaced with starting the emulator. But from the top level, they should look aligned.
Yeah. Sorry, my question is more about injecting that new, injecting the constructor into the factory, so that the fixture is generating the instantiation of your unique device adapter subclass.
Yes.
Right.
Yes, I believe it should be easy.
Okay. We could chat after.
Yes.
Thank you. That concludes this session.
Thank you.